Uh, Asim, can you see the blackboard?
Yes, sir.
Is it
Yes, I can
totally
see.
visible? I'm
Yes,
trying
sir.
to push uh,
But
my laptop a little backward so so people can see the blackboard, and I hope
yes,
they
sir.
visible for me.
Yes, sir. ठीक थे बिल्कुल बराबर है बस.
Right. So last time, right? Uh, So last time we were doing the permutation operator. Someone wants to join, and who is Kamal Shah? Okay. So last time we did the rotation operator, right? If you remember, we were doing last time the rotation operator. Last time we discussed the rotation operator, right? And we denoted it by R, right? If you remember, we okay. If you remember, we said if we rotate a three-dimensional system, right? About if we have a three-dimensional system, uh, I, J, and K, right? And suppose we rotate about I, and we rotate about in the anti-clockwise direction, right? So, and suppose we rotate it by 1 over 2 pi around the unit vector I. And if we say the unit vector I, we represent it by H1, right? This was I am just uh, trying to connect to the previous situation and to resume what we did in the last lecture. And suppose we say we have a three-dimensional coordinate system. So J would be like 2, right? And K is suppose represented by Sanket 3, right? And we said that if we have a system like this is suppose I and is equivalent to 1, right? Is the board visible and the writings are okay? Asim?
Yes, sir. Yes, sir. Okay.
Okay. So we said that is I, then this is J, and this is K, suppose, right? The system. Now we want to rotate this system. It's like this. This is Y, this is Z, and this is X. So X is perpendicular to Y and Z. So we are rotating, there is a rotating operator and rotation by pi by 2 around the x-axis. And we call x-axis by k to 1. So we rotate it, suppose by uh, pi by 2. Right? Then, suppose we apply the rotation, right, to to kind of a vector. Suppose that is like 2 plus 3. Suppose we apply the rotation operator to this, right? This is some vector. Suppose that is, we say, that is like 2 kit, and that is kit 3, right? So we want to apply the rotation operator, right, to this combination, right? So what we gonna get? R, right? 2 plus 3, right? We said, so this can be written as R is applied on 2 and R is applied on 3, right? Okay, so suppose this equation 1. Now, here, what is R when we apply it to 2, right? Which means that R pi by 2 around the kit 1, right? And this operates on kit 2. Right? Okay, so look, if suppose this rotational operator acts on this and it rotates it clockwise about this axis. This is x-axis. My thumb is representing x-axis. So you are rotating this vector 2 around my thumb in this direction, anti-clockwise direction. Now you will see that this will become 3. You are rotating this. This is a unit vector. You are rotating this. So after 5 by 2 rotated, it will become this. So when this R works on 2, it makes it 3. Right? Similarly, now when R acts on 3, right? So what will be the situation? It's like this. You are rotating 3, this is 3. Let me give you some good explanation to make it clear. This is x and our vector 1, and this is 3. So you rotate this anti-clockwise by 2. So it will become like this. So this is 2, and this will be minus 2. So when this rotation, which we have defined it like this, when we apply this to scale 3, it becomes minus 2. Right? So we see that when we apply, when we put this 2 and 3 in 1, right? So R of 2 plus 3, this operator is equal to that is look 1, 2, sorry, 2 and 3. This is 3. So it will be equal to, we can say it is equal to, we can say minus 3 or minus 2, 3 and minus 2, right? So when we look at this, it will be like this thing. If this is 2 plus 3, if we apply this whole to here, it gives you something like here. Right? So if we apply to this vector, suppose the rotation operator, it brings it pi by 2 here. And similarly, it has two components. One will be like, this will be like 3, and this will be like minus 2. So it means that applying this R rotation operator, 4 will solve it, right? That is 4, right? 1, 2, 3, 4. We apply it this way, or we apply it this way. We get the same result. Look, we apply it here, and we got the right hand side. It's like this, you know. You put this in 1, and left hand side is equal to the right hand side, and therefore this operator is leading. This rotation operator is right. This is equal to R2 plus R3. Look, we got it. We put these values here, right? Okay. If you apply this, if you want to see here, this is 2 plus 3, right? And it gives you the same thing. So that is an example of our explanation of the situation, right? Generally, this will also be like if you apply this whole and rotate this 2 plus 3, this by 5 by 2, right? Look at this. Minus 2 plus 3. So you see that from 4 and 5, this is a linear operator. Remember, what I want to say at the moment, that you must be comparing my notes with the book. You know, I can do mistakes. So always compare my notes are the class notes with your book, and always do a correction, right? And discuss with me if there is a discrepancy between the book and my classwork. Okay. Look, if generally we have a kit I, some kit I, right? And suppose an operator omega acts on it, right? So we will say omega acts on this operator, some operator I, sorry, some vector I. Omega is an operator, and I is a vector, right? Isn't it? So it actually turned it to some other, right? Right? After rotation, you know, 3 became minus 2. You saw it. So it makes it some other kit. After okay, in the same manner, suppose we have a vector V in an n-dimensional linear vector space, right? then we can represent V in terms of its components, right? That is equal to Vi into I, where I is a basis vector. We have some basis, and I is a basis vector, right? Okay, if we apply an operator omega on it, right? So we say this omega applies to this thing, Vi into I. I starts from 1 and goes to some n, right? And since this Vi is a scalar quantity, so we say that is equal to Vi, and it will be omega into I, right? It's all this equation number 1, right? So we know from equation number 1 that this is equal to, right? This is equal to, where that was here. This is equation number 1, right? So we know that omega I is equal to I prime, right? So if omega operates on a vector, it actually operates on the basis vector, and changes that operator changes the basis vector, right? Changes, bring it into the new basis. Right? Like in the previous case, suppose we have, if V is equal to, V11 plus V22 plus V3 into 3. That is a general case. V. And these are the components along one dimension, component along the other dimension, and component along the third dimension. These are the components. These are just scalar numbers, right? These are kids, and these are scalar numbers, right? Okay. So when we apply rotation operator to V, right? It will be like you apply this to this whole stuff. Right? So it will be like R into Vi1 plus R into this is not Vi, V1. This is V1, not Vi, sorry. This is V1. So V1, and this is V2 into 2 plus R, V3 into 3. Right? So we know this when R is acting on, when R acts on this, we saw that actually it will act on V1 will remain here, right? And it will work on this R1. So this will be equal to V2 R and 2 plus V3 R and 3. And you know, the rotation is about I vector or X axis or this kit 1. It is about this in the previous example. So it does not change it. When you rotate about this, my tongue, so it is not doing anything to my tongue. So it will be the same thing. So V1 and it will be 1. Right? And we say that V2 and it makes 2 into, it turns 2 into 3. We saw that in the previous example. So there will be 3. And we saw that this turns 3 into -2. So it will be minus V3. So this is how a rotation operator about, right, 5 by 2 about kit 1 will be acting on a vector which has components, right? V1, V2, and V3 along the t-axis, right? Now let us see how we deal with product of operators. Now, the product of two operators, right? Suppose we have two operators, lambda and omega, right? So when if it is applied to a vector V, right? So what is the situation then? Right? So it will actually act on the kit in its own order, right? So first, this omega will act on V. So we can say this acts on kit V, right? We say it turns it into V prime. Lambda is another operator, right? So it turns it into V prime, right? Okay, we can check that in terms of omega lambda, right, will be different. If you apply this, then omega is here, right? Omega is here, and lambda will first act on V. Now, it will be omega, and this is a different operator. Lambda is something different. So it will not turn into V prime. We'll suppose it turns it into V double prime. It will turn it into some other vector, right? So it will be like something different. So these two operators, the question 1 and 2 are generally not equal. Not equal. They are generally not equal. So we say that omega lambda, right, is not equal to lambda omega. Generally, they are not equal. And so, what is the difference? If they are not equal, we are interested in to find out what is the difference, right? So, the difference will be omega lambda minus lambda omega. That is equal to what? Whatever it comes out, right? We call it this thing we call the commutator of omega and lambda. This thing, whatever the quantity is, we call it the commutator of omega and lambda, right? And it is represented by by putting in these two brackets, right? Omega, comma, lambda. We call this thing as this, right? This is equal to the commutator of, and this shows us the difference between the two operators when they are applied in a different way, or in, we can say this, when they are applied in reverse order. First, this one is acting here, and then this one. And suppose first lambda is acting and then omega. So what is the difference? That difference we call it the commutator, and denoted by these two operators omega and lambda. They are enclosed in brackets, right? Okay. Now there are some important identities that we will be using in our some important operators, yeah, that we will be using in our coursework later on. So we have to remember. So that if you remember that these are operators. Operators could be like derivative is an operator. If you take the derivative, of a quantity, like that is an operator. So if we have B and C operators, right? We know we have talked too many times about this, the methodology of quantum mechanics. We said this is like a language. And in language, we have to remember different grammar rules. And we will use this language to solve our problems of quantum mechanics, right? So for this purpose, we have to learn the language. We have to memorize the grammar. We have to memorize the vocabulary, different things. So we have to memorize them. So if A, B, and C are three operators, right? Then if we have something like this, right? There are two operators in a product form, and we want to find if their commuter with the third operator, suppose C. You want to know this, right? So that can be equal to, right? A and to B and to C, right? Plus A, C, and to B. Suppose these are operators. So if this depends upon the order. In generally, here lambda omega is not equal to omega lambda. Here, if it is here in the first position, that is different from if it is in the second position, right? So here, if we want to find this commutator, right, in which the first operator is a product of two, then we have to find the commutator of the two laws first, and then apply it here. Remember, the order is important. Remember what? The order is very important. The order is very important, right? So मुझे ये याद नहीं आता आमतौर पर. This is very difficult. मैं तो हमेशा भूल जाता हूँ. So you have to remember this, right? So will it be easier for you to remember, Asim?
Yes, sir. Koshish Baku.
Okay. Will it be easier for you to remember?
Yes, sir. It's easy, sir. This
Okay,
one is
hope.
easy.
Okay, okay. Hope that your memory is very good. My memory is very poor. I just do it like this. I use a trick in my own mind. You know, I am sometimes confused if it is C should be first or B should be first, or A should be here or here, or B should be here or here. This confuses me a lot, and I cannot remember this. So I say it is like the derivative operator, if you remember that, right? Derivative of f and g, they are two functions, right? So we say first. I remember that when I was a young man, of in my FSC and my 12th grade and my 13 and 14 grades, it was easier to remember formulas and different things. And we would say first function, derivative of the second function. So I would say first function, derivative of the second function. Right? So it is like this. Look, first function, derivative of the second function. Like this. First function, A, derivative of the second function. Plus, we will say second function, G, right? And the derivative of the first function. Right? This is kind of a rough trick to remember for me. You might be very good in remembering them. But for me, it is like this. So, it will be like this. Look, there is the first function and the second function. Sorry, yeah. And the third function. Am I right or not? Kind of. I hope so. First function and this right plus is it plus? मैं थोड़ा सा गड़बड़ है मेरे सामने मेरी वायरस में. We have to do it like just I am giving you a trick to remember it. Maybe it's easier for you to remember. For me, it is usually difficult. So, first function A and A. Okay, this is A. Yeah, this I would say this is here. What? This is A, and that will be my B, and then G will be my C. So first function. So it is not like that. If I say A, so whatever. I will again. I don't want to waste a lot of time on this. I will see the argument later on myself again. Right? Don't take this thing very serious. I was trying to make it trick so we can remember what we have said there, right? That is why I said, oh, we can remember it like that. So derivative, first function, and that was A. And here is not. So its first function here is like this thing, right? This is my first function. But and then when you hear my first function, this is B. And this is C. My first function, the derivative of the C plus. So that is 3. So isn't it you know here this has to be on the other side. Right? This has to be on the other side. Yeah. This is not working very much. So don't stick to it. You can make your own trick by looking at this. I will in a leisure time, free time, I will try to recall how did I give in my notes this example. Anyway, if we have This is not good. Not good cleaning. I will use this. This good. That's good. This is good. Okay. So we would say if we have something like lambda and omega and theta, right? We have three operators and a commutator of these two such that the first is itself, uh, right? A product of two other operators. So we will say we will take the first, right? And we will say this thing, the commutator of these two, and we should keep in mind that this is operating on these two, therefore we will put it in front, right? Then we will say that the second, this operator in God, the term of these two is gone now, the commutator of these two is gone. Now we have to take the commutator of the other two, right? The commutator of the lambda and theta, right? So commutator of lambda and theta, right? And we should write omega after the commutator. I personally, try to remember that this omega is not here because here lambda comes first, and since we say that order is important, so just to keep in mind that lambda should be first and omega should be later on. So kind of just to remember them, right? And if we have something like this, right? Omega and to lambda theta, right? So we write lambda, right, and omega and to theta, right? Omega actually acts on this function, right? And then plus omega acts on lambda, or commute with lambda, and then theta. So suppose this is equation number one, this is equation number two. Right? They are not equal. Right? Here, the difference is the main difference is here in the second situation. Right? So let us go forward again. Okay, I made that for what I kind of recall the product group, but you have to. This does not apply by some the term that does not apply to this. Look, like derivative of I'm taking these are functions, so they're generally not functions, should be operators, but I'm just trying to connect it to my previous formula memories. So it would be like derivative of the first. So here there are two. This is here, and this corresponds to this, suppose. So look, derivative of the, we say first. So first here, these are two. So first is lambda, right? First, and we say derivative of the second. Right? First, derivative of the second. Plus, we say second right? So secant will be G, right? Which will be theta. So I will say it should be like G, right? And derivative of the first, right? So it is kind of like this, you know. This is okay. Here is the difference. G is here in the second. It is in the it coincides with theta here, right? So from our very old formulas of the chain rule or the product rule or the chain rule, right? This is the chain rule. So G comes here, but since we say since this is operator and not a function, right? And G is for theta. So we cannot switch. It is the order of this is first. We cannot put this ahead because these are operators. We should keep the order. Therefore, we should put G from here to here. From here to here. This is how I remember. You know. So it is then it coincides with this. This is then okay. And you know. It is it is kind of a waste of time if you can remember it without any hints, right? Okay, so okay, inverse, right? Inverse of omega, right? So if we the product of inverse of omega and omega, right? So we say omega and omega inverse, right? That will give you the identity operator I, which we have already done, right? And right, we will say if we have an operator R pi by 2 into I, right? That's an operator. We rotate it in clockwise direction. Now its inverse will be to rotate in the anti-clockwise direction. So R minus pi by 2 into I will be its inverse, right? Okay. If we have inverse of a product, inverse of a product. What? If we have inverse of a product. Are you with me? Everybody with me? Asim? Are you?
Yes.
Is it
Yes, sir.
okay?
Yes, sir. Okay.
Okay. So if we have a product, right? Of two operators, omega and lambda. If we have product of two operators, and we want to take inverse of it, then will be just we have to take the inverse and change the order, right? So it will be like lambda inverse and omega inverse. Change the order. Take the inverse separately. You have to remember all these. uh, So if you have a product of two operators and you want to take the inverse of it, you just change the order, right? And take the inverse separately. Then that will be the answer to the problem, right? Now we want to Let me know if you have any question.
Sir, why order changes of the operators when we took inverse of these two?
Okay, try to remember. I told you that you have to go back to your home and your mathematics classes and to learn matrices. So we present an operator by a matrix, and
Yes.
matrices have the same rule. If you take the product of two matrices and then you take an inverse, then that is equal to the inverse, the product of the inverses are both separate. You can prove it by taking two matrices, right?
Okay, okay, sir.
आप कोई 2 by 2 matrices ले लें 1 2 3 4 ये एक मैट्रिक्स हो गया 4 5 6 7 ये दूसरा हो गया then just put the product, right? Take the inverse and separately take the inverse of each and then make a product and you will see that they will be equal, right?
Okay, sir.
Yeah. Okay, matrix. How do you find matrices representing operators? We want to find to represent specific. We want to find matrices that will represent specific operators, right? How can we do that? It is like okay, we are finished now. We know, right? We know that a vector can be represented by a column matrix. Right? Vector can be represented by a column matrix, right? And a matrix has just numbers. So we say a vector can be represented by just an array of numbers, right? In the form of column matrix. Similarly, an operator can be represented by a matrix with just numbers. And is in the vector case, all these numbers are the components of that particular vector along each dimension in the basis. We have done that. Similarly, what will be the situation? What will be the shape of a matrix if it represents an operator? Right? Let's do that. So that will be certainly, if we have a column vector, right? N rows, n dimension, right? So if we multiply it, right, with a row, we get a scale, right? R, since it is an n by n matrix, so there will be kind of the components, the number of components of a matrix will be n squared. If a two-dimensional base, if we have a two-dimensional base, right, then there are two components of a vector, I and j. There are two components of a vector, I and j, along I and along j. Some quantity, some projection of the vector along the x-axis, some projection of whatever vector we have along the y-axis. So we have two numbers to represent a vector. And to represent an operator, right? An operator will be like two matrices may be defined in reverse order multiplication, right? So it will be an n by n, matrix, right? Something like that. Okay. Suppose we have I prime, right? Right? And we have some I, two different bases. two different basis vectors, I and I prime, right? Suppose we apply an operator to I, right? And change it. Suppose it changes this operator changes the hit into I prime, right? So this is we have, if we apply this to a vector V, if we apply it to a basis vector, then this is the situation. It changes the basis vector to some other form. If we apply it to a vector which is defined in a basis, which has some components in a basis, right? And then will be omega, the operator, right? And it will be like this vector has some components along the basis vectors. So we say Vi and I, right? 2j are 3k plus 3k, 2i plus 3j plus 9k, something like that. So these are just, the VIs are just numbers. And then these are the basis vectors like ijk. So this can be written as Vi will be spared because it does not act. It is a scalar quantity, and omega, right? And it acts on. So we say that how this operator acts on. Remember, we are going to find a matrix form for an operator. So we do this exercise for it to find the components, of a matrix given in a basis of some dimension of n dimension. How do we find different components? How we represent an operator in matrix form, a certain operator. For example, your rotation operator, we just discussed. How can we represent that rotation operator, which we just did, the example we did? How can we do that in the matrix form? Matrix form में हम इसको इस तरह लिखेंगे, right? So that is equal to here Vi, and remember from here it is equal to I prime, right? So अब हमारे पास मसला ये है, look, we apply this omega to V. This is an operator. It acts on a vector which has components along an original basis I. Right? Like this. This vector has components along, some components along I. So we got those components, but we got a new vector. Now we have to find how the operator is related to I prime. What is the form of the new basis vector? ये new basis vector क्या है? ये जो हम यहाँ पर लेते हैं, this is the result of the operator which is acting on some vector V is given in a basis. So we saw that it is equal to whatever the scalar numbers are, जो पहले इसमें दिए गए हैं original में, and a new vector, a new basis vector, not vector, a new basis vectors, a new ijk, right? So people have to find what are those new basis vectors, what are those new ijk, right? So let us see, right? Suppose we have an inner product of, we want to find, okay, we have two bases. One is the original basis, and then we got another basis, this I prime kit. which is given by which is made by the operator omega. It is given a new basis is given to us. New basis vectors are given to us. We want to find the new basis vector in terms of the old basis vector. We have to find them in terms. For example, हमारे पास ये जो है हमारे पास axis पे, right? So we have these basis vectors, right? I will say I, J, and K. I, J, and K. These are three basis vectors. Now I am applying some rotation operator, right? So we say if I apply a pi by 2 rotation about the axis I, which is this one, right? It will be kind of like that. So these are now the new basis vectors. This, and this. These are now the new basis vectors. We want to find now what is the relationship of these new vectors with the old. Or if it does not rotate it about pi by 2, if it rotates, if the rotation operator rotates it by any angle theta, for example, this 45 say, if the rotation operator rotates it by angle 45, something like this. It was like this, right? First. So if this rotates, it's the rotation operator by 45. So it will be kind of like this. Now you know this vector has a component. This is a new basis vector, a new basis, एक नया set. So this has a component along the old. It was this thing. Similarly, this has a component along the old, which was this one. Similarly, this has the component along the old one, and this. So all these new vectors have components along the old vector. So we will define these new basis vector in terms of the old vectors that we know, right? So what is the transformation? We have to know the transformation between them, right? The transformation between the basis vectors. दो systems को हमने पहले एक system of coordinates को दूसरे system of coordinates में डालना है. We have to find it, right? So for that we want to find the dot product. We know that the dot product gives the projection of the component of one vector along the other, right? So the projection of this, which is new, along this, which is old one. I am just labeling them. These are the old. The J is just a label. It is like I or whatever if you call it. आप I भी इसको कह सकते हैं, लेकिन this is prime, which is new. This is unprime, which is the older one. I'm calling it J because not to confuse. So, okay, so that will be equal to J, right? And I prime was equal to, what was I prime equal to? Omega I, right? It was equal to omega I. And if this, okay, we call this as, right, matrix element. Matrix element of the operator omega. We call this thing as matrix element. जो matrix elements हैं, जो matrix the numbers, all these numbers they of a matrix, they are called the matrix elements, right? So they are the elements. So this is an element of the matrix which represents what? Which represents the operator omega. And we will represent this product, this kind of product, the scalar product, We represent it by omega I and j. Right? This is the matrix element of the matrix which represents the operator omega, the subsurgent operator, right? And these are all the elements I and j, right? And I and j are the basis vector. I prime here, it was the nucleus. I j broad represents the all basis, right? Here we do it in the form of the known, right? These are I and j are the unprimed coordinate system. So we know them, right? And then we know its action on it. We know its you have to know the action, right? Just have to by force rotate. So we know the action. So this is known. This would be known to you. A element you have, for example, this is omega ij. So you can have, if this is 1, right? If this is 1 and this is 2, if this is 2 and this is 1 or something, right? You can call it the okay. R, this is like draw, right? Which is kit column, number of rows, number of columns should be like J, I believe. Then we will have to check it. Okay, you check it. I don't have the book at the moment, so you can check it. Okay. So we know this, right? We will know like omega 1, 1. They will be like omega 1, 2, omega 1, 3, omega 3, 1, omega 2, 1. All these are elements of a matrix. And remember, I told you matrices are very important, and we will have to do the matrices. Okay. So again, let us do an explanation for this through examples. Okay, like we have a vector that has been changed, right, by an operator, and it turns it into B prime, right? And we know that B prime, that is the new bit, they will have some components B I prime, right, into I, right? Components of the vector along I, right? Okay. And we know that V I prime will be equal to I, right? And to V prime. That is a vector. V prime is suppose a vector. Suppose the components along the all bases, they are Vi prime. These are the bases, that's the basis. I starts from 1, goes to n, right? 1 is each. So the component is by the projection of that vector along the different base vectors. We say that's a scalar product, right? So that is equal to I and to omega and to V, like this. Right? So that will be equal to I omega, and V will be equal to Vj, right? And sum J, right? J starts from 1 goes to I. The J is just another label, you know, you don't have to worry about it. Could be I, but just not to confuse you, right? So V is L is the component of V along the same basis. You know this the same basis we are talking about. So that will be equal to, right? If this is a scalar quantity, so we can bring it here, right? And we say Vj, and that will be equal to I omega into J, right? And here it will be equal to, right? J starts from 1 goes to n, right? This Vi prime. The component of the vector after rotation along the OR basis, right? So Vj, which is the scalar quantity, and we call it omega ij. This is what we did, right? So if this is 1, right? This is now 2. So the component of this vector along the OR, you can get it by component of the matrix and the components of the original vector before the operation in the same dimension, in the same basis vectors, right? This is V prime equal to, right? R, since this is a scalar, so we can bring it here or here without any problem. So let us write in this form, right? And remember, this is J, the J value is here. So Vi is equal to, right, omega I J, and then the J. Transfer from goes to and V J. Right? This is a question. We get the components, right? Of the new vector. We can find them by this situation, by this expansion. Right? We can write this in matrix form. No? This will be a column vector as we have done. So it can be written like this. Vi, so V1 prime, V2 prime, Vn prime is equal, right? This thing can be written in the form of the product of two vectors. What are two like this? Right? We will write like this. Similarly, 2, 1, 3, 1, right? And another 1. So if you look, these are this is when you omega 1 will be the transform basis. Omega 1 again, that is the omega 1 is the transform basis, and these are its components along the when you scale over the other components. Right? This is actually that 1 prime. This is what I write it. It will be like this. That 1 prime. So it is the first column of this operator is actually the components of the first transform basis in terms of the older basis. Right? Okay. Similarly, this one that will be 2 omega and so on. It will be n omega and that will be this and will be v1, v2, vn. Right? So this I starts from, you can change I equal to 1. So you will get this. If for I is equal to 1, it will be v1 prime is equal to the product of this row with this whole column. And the product of this row with the whole column will give you this thing, omega ij, which is this one, and vj. So this one, we call it, if you remember, we call it like this. This is suppose the same thing, and we will call this, if you remember, we call it omega 1, 1. Similarly, we call it omega 2, 1. A number, this omega 1, 1, omega 2, 1, they are just numbers. And similarly, this will be omega n 1. Similarly, it will be omega 1n, omega 2n, and go on omega nn, and v1, v2, vn. Right? So look, v1 will be, v1 prime will be equal to, v1 prime will be equal to the product of this whole row with this, and this will be omega 1, 1, v1 plus omega 1, 2, 2, 1, v1, v2, and plus the other one, plus omega n, vn. Omega n, 1 n, omega 1 n, vn. So it is by just putting I is equal to 1 and varying j, you get the first. Then putting I is equal to 2 and you get this thing. So this equation can be represented by this matrix equation. This is how we represent an operator. Right? So this is the operator matrix, and this is how we get the new component, the new vector, right? By applying an operator on the old vector. Hopefully, we want to do some more work on it. We'll do something more on it, and it will be explained more. We do your homework. And if you have any questions, you can ask me at this time. How many people are here? Only 11? And no, probably how many? 11 or something like that. So if you have questions, let me know. Otherwise, I'm going to stop it here. Any question? Asim? Asim, any question? I am just stopping it. Okay, if there is no question, I will stop it. Thank you. Thank you for listening. Okay, see you tomorrow, hopefully.